Hi everyone. Today I'd like to go through this problem with you guys. We're going to go through it step by step and make sure that we check the official FE reference handbook to find the appropriate formulas. Let's get right into it. It says a rectangular column with a cross section of 5 by 3 centimeters is to be assessed to find the critical buckling load. If the length of the beam is 4 meters, the critical buckling load is most nearly. If you look in the image, we also see an elastic modulus is given 30 GPa. Let's go ahead and compile some of that information. Firstly, we know that the cross-section was given to be 3 by 5. Let's call the 3 side A and the 5 side B. And let's assign an axis over here. An XY axis, where Z is out of the page. When that critical buckling load is applied, we can buckle about the Z axis, and I've drawn the deflector shape on screen. In this orientation, the Z axis would be pointing towards the left, the Y axis would be up, the X axis will be out of the page. We could also buckle here about the x-axis. So we really have two options here, and we're not sure of which one will produce the critical buckling load, the smallest buckling load. In the z-axis orientation, something else that we note is that the n-type is a pin-pin connection, which is relevant here. That modifies the effective length of the beam. And buckling about the x-axis, we know it's a fixed connection. You can see it here. It's not pin-pin, it's fix on the ends. I have the formula here from the reference manual. Page 137 of the reference manual under the section labeled columns. We have a critical buckling load formula here. This one is fine, but I prefer to use the critical buckling stress because it has this dimensionless term in the denominator called the slenderness ratio. You know that a beam will buckle if it's slender. Slender beams have a larger slenderness ratio, which will produce a smaller critical buckling load. So all we really have to do is compare the slenderness ratios about the z-axis and the x-axis to find out which axis it will buckle about. We also see some K values here for the pin-pin and the fix connection, and note that the radius of gyration is just a square root of I over A. Now we have this information, as well as we're going to need to find the moment of inertias of the rectangular cross-section about a few different orientations. So let's note that information here on page 98 of the reference manual. The moment of inertia about the x-axis. If we're looking at the x, the single term is going to be that b term. If we're looking about the y-axis, the single term is going to be that h term. You can see it's parallel to the y-axis. That's why the single term is the h. Here, parallel to the x-axis is the b. That's going to be important for us. So the critical buckling stress, or the critical buckling load, which is just a critical buckling stress sigma times the area, that's equal to pi squared E divided by the effective length divided by the radius of gyration squared. We take that entire term, the critical buckling stress, multiply it by the area to find the critical buckling load. We know that what's going to be of interest to us is RZ, which is just the square root of IZ over A, as well as Rx, which is the square root of Ix over A. If we draw out our axes here, this axis here is going to be the x-axis. You can see the x-axis is parallel to this long side, which is 5, and perpendicular out of the page in the front view is perpendicular to this axis. We know that IZ Let's move this stuff over. If we're looking at IZ, that base term is going to be this A term over here. It's going to be AB cubed over 12 divided by AB, the square root of this entire thing. What about for RX? IX, again, parallel here, parallel to the x-axis is that B, that's going to be the single term. That's the BA cubed over 12 divided by AB, the square root. If we reduce both of these terms, what we get here is B over the square root of 12, and what we get here is A over the square root of 12. Let's plug these values into their appropriate slenderness ratio. Again, we're looking for that effective length, that K times L. We know K for a pin-pin connection is 1, and K for a fixed connection was 0.5. Overall, the slenderness ratio is L effective divided by the appropriate radius of gyration. We have what the radius of gyration is on the right. So this term, remember that L effective was K times L. So that means it's just L here. The reciprocal of the radius of gyration is the square root of 12 over B. How about for the fixed connection? We have L effective divided by the radius of gyration about the x-axis. The effective length is 0.5 times L for a fixed connection. 0.5 times L. And the reciprocal of Rx is going to be root 12 over A. We want to compare these two slenderness ratios. Let's plug in what A and B is. We have L root 12 over the B value was 5. And here we have L root 12 over, we can take the 2 and put it in the denominator, so this is just 12 over 4. That's the square root of 3. Divided by the A term is 3. So which one is greater, the x-axis or the z-axis? We can see that about the z-axis or the pin-pin connection, we have a larger slenderness ratio. So that means it's going to buckle about the z-axis. Let's go ahead and plug in these numbers to find the critical buckling load now. P critical, which is equal to pi squared EA divided by the effective length, which is just L for the z-axis, divided by the RZ term. We have already what L over RZ is. It's just 0.69 times L. Let's go ahead and plug that in. So we have 0.692 L in the denominator. We square that term. Pi squared. We have the E, which was given to be 30 GPa. And we have the A, which is just 5/3. Let's work out some of these units over here. You can see that the choices before, if you recall, were in kilonewtons, so this is around 5.8 kilonewtons. We could plug this back into the app here. If you're interested in my app, the link is in the description. Check the answer and it's correct. You can see that I have a written out solution here if it's more concise for you to read. Now, if we just quickly kind of think through the solution, what we did, we had two options that the beam could buckle about, the z-axis or the x-axis. We compared the beam to see which one was more slender. We looked at the slenderness ratio, which took into account the end conditions and the radius of gyration. Comparing those two, what we saw was that buckling will occur about the z-axis, which was the pin-pin connection. Then we computed the critical buckling load and got around 5.8 kilonewtons. I hope this video was helpful to you. Please like and subscribe. I'll see you in the next video.